Hello everyone and welcome back to the Calculus video lecture series. Today we are going to be covering the derivatives of the inverse trig functions, which will be the last of the derivative rules that we are going to be covering in this course. So we're going to start off with the derivative of the inverse of a function f of x in general, and this applies to any one-to-one function f of x that has an inverse that exists. So let's say that f of x is differentiable and is one-to-one with an inverse g of x equals f inverse of x. Remember, this notation right here does not mean f raised to the power of -1. This just stands for the inverse of f of x, which just for simplicity we're going to call g. If b is some point that belongs to the domain of the inverse function g of x, and the composition f prime of g of b does not equal 0, then the derivative of the inverse function evaluated at b is going to equal 1 over f prime composed with g of b. So, for example, let's say that the function f of x equals square root of x plus x squared plus 1. Let's say that it is 1-to-1, which means that it has an inverse. And it has an inverse on the interval x is greater than or equal to 0. What we're going to do is we are going to find the slope of the curve of y equals f inverse of x at the point 3, 1. Finding the slope of the curve, also known as find the slope of the tangent line, means find the derivative. So we are finding the derivative of f inverse of x at the point 3, 1. So we're basically finding the derivative of f inverse of x evaluated at 3. So, according to the theorem that we just covered over here, the derivative of the inverse evaluated at b is going to be 1 over f prime composed with the inverse evaluated at b. So the f inverse, its derivative evaluated at 3, is going to be given as 1 over the composition of f prime composed with f inverse of 3. F inverse of 3 we can actually find pretty easily because we know that the point 3, 1 is on the curve of f inverse of x. So we already know that on the graph of f inverse, the y-coordinate that goes with 3 is 1. So we already know that f inverse of 3 is equal to 1. So this will simplify down to 1 over f prime of 1. And since we were actually given what f of x was, we can easily find f prime of 1. So you can either do this on a calculator or you can do this the long way by hand by taking the derivative. So the derivative is going to be 1/2 x to the power of -1/2 plus 2. Then f prime of 1 is going to give us 5/2 when you plug 3 in for x. So 1 over f prime of 1 was 5/2. 1 over 5/2 gives you 2/5. So the slope of the tangent line of f inverse at the point 3, 1 is equal to 2/5. Now, one of the uses of that theorem is to find the derivatives of the inverse functions evaluated at specific points when either finding the inverse function by itself is either not possible because you don't have an f of x or not very easy in a case like this. There is another use for this theorem, and that is in the derivatives of the inverse trig functions. And if you look at the derivative rules sheet that I posted on Canvas, you might notice that if you look under the inverse trig functions, that the derivatives of the inverse trig functions are not trig functions. The reason why is that theorem. So we're going to apply that theorem for the function f of x and its inverse g of x, which is sine inverse of x. So the derivative of sine is equal to cosine. So the derivative of sine inverse of x is going to be 1 over the derivative of the original function composed with the inverse. So the derivative of sine inverse of x is going to be 1 over the cosine of the sine inverse of x. Now, if you let the sine of theta equal x, and theta equals the sine inverse of x, what you can do is you can draw a triangle with a theta in which the sine of theta is equal to x over 1. A little Pythagorean theorem later gives you an adjacent side of the square root of 1 minus x squared. So the cosine of this angle theta, if you let sine inverse of x equal theta, is going to be the adjacent side, square root of 1 minus x squared over 1. So overall, the derivative will be 1 over square root of 1 minus x squared. I'm never going to ask you to replicate any of that. That was just an explanation of why the derivative of sine inverse is 1 over the square root of 1 minus x squared. Then the derivative of cosine inverse is going to be negative 1 over the square root of 1 minus x squared, and its proof is very similar. And then for the other trig functions, the derivative of tan inverse, which is another one that you really should know, you are going to be using tan inverse quite a bit, is 1 over x squared plus 1. Derivative of cotangent inverse is negative 1 over x squared plus 1. Derivative of secant inverse is going to be 1 over the absolute value of x times square root of x squared minus 1. Derivative of cosecant inverse is negative 1 over absolute value of x times square root of x squared minus 1. So if you want a reference slide, these are all 6 of the inverse trig functions all in one slide. They are also on that derivative rules sheet that I posted on Canvas. So what we're going to do is we are going to use all of that to calculate df dx evaluated at x equals 1/2, where f of x equals arcsine of x squared. You might remember from pre-calc when you learned about the inverse trig functions that arcsine is just an other notation for the sine inverse. So arcsine, sine inverse, they mean the exact same thing. Arcsine just avoids the confusion of thinking that this is actually an exponent of -1. It's not. This is not just 1 over sine x. This is not sine x raised to the -1. This is inverse sine. So because that can be confusing sometimes arcsine x is an alternate notation. But anyway, we're going to evaluate this and we're going to leave our answers exact. Now, because the question is asking us to leave our answer exact, we cannot use a graphing calculator because a graphing calculator will give us a decimal approximation, which is not an exact answer. So if a question asks you to leave your answer exact and you do not leave your answer exact and you give a decimal approximation, you get no credit for that question. So unfortunately, we're going to have to evaluate this by hand. So I'm going to first find the derivative function, arcsine of x squared. Now, anytime that you have anything other than just x inside any of your inverse trig functions, you will need the chain rule. So the outside function is going to be this arcsine, and the inside function is going to be x squared. Now, for the derivative of the outside, this is what the derivative of sine inverse of just x looks like. So the derivative of sine inverse of just x is going to be 1 over square root of 1 minus x squared. Now, if you have the derivative of sine inverse of a function of x, the derivative of the outside will be in this format, except where you see that x right there, you will put the inside function left alone. So the derivative of the outside will be 1 over the square root of 1 minus the inside left alone squared. And please use parentheses around the inside function. So the derivative of the outside is going to be 1 over the square root of 1 minus the inside left alone with parentheses around it squared. So that's the derivative of the outside. Then we're going to multiply it by the derivative of the inside, which is 2x. And then just because we're going to have to evaluate this at a particular value and do a lot of simplifying to leave our answer exact, I'm going to simplify this a little bit just for the sake of my sanity. So I'm going to put this 2x in the numerator, and then in the denominator, this x squared, you can multiply the powers, it's x to the 4th. So then if you're going to take this derivative and then evaluate it at x equals 1/2, you're going to take the derivative function and plug 1/2 into every single spot that you see an x. So the numerator is going to be 2 times 1/2 all over the square root of 1 minus parentheses 1/2 to the 4th. Now 2 times 1/2 is 1 over the square root of 1 minus 1/2 to the 4th. If you take a fraction and raise it to an exponent, you just take the numerator and denominator and raise that to that outside power. So 1 to the 4th is 1, 2 to the 4th is 16. Then this is a complex fraction, so I'm going to do that subtraction inside of that square root with common denominators. So 16 over 16 minus 1 over 16 is 15 over 16. And because 1 can be rewritten as a square root of 1, the square root of 1 is itself, what you can do is you can take this expression and you can actually simplify it using the same rules as other complex fractions. So you would leave the numerator alone and you would reciprocate the denominator. So you can actually write this as the square root of 16 over 15. When you have a square root inside of a fraction, you can simply take the square root of the top and the square root of the bottom. Square root of 16 is 4. 15 has no perfect square factors, so it is fully simplified. And if you need to rationalize this, you just simply multiply both the numerator and the denominator by the square root of 15. So your final answer is going to be 4 square root of 15 all over 15. So anytime that we're supposed to leave our answer exact, we need to make sure that we are doing this by hand. A calculator will not give you an exact answer. So then for these next two, these are going to be, derivative functions, so we won't have to worry about leaving your answer exact here, but we are going to be taking their derivatives using chain rule. So we have first the derivative of the sine inverse of x squared minus 1. So since we are taking the sine inverse of something other than just x, this is going to require chain rule, where the outside function is the sine inverse, and x squared minus 1 is the inside function. Now remember, this right here is the derivative of the sine inverse of just x. If you have a composition, the derivative of the outside will be 1 over the square root of 1 minus the inside left alone squared. So the derivative of the outside here is going to be 1 over the square root of 1 minus the inside left alone with parentheses around it squared. Then you are going to multiply it by the derivative of the inside. Derivative of x squared minus 1 is 2x. Now, no, you cannot cancel out that square root and that square because of this minus sign right here. If you wanted to expand out x squared minus 1 and maybe combine some like terms, you could, but realistically, it doesn't really simplify that much, so this is good enough. Now for this next one, we're going to be taking the derivative of the cosine of the sine inverse of x. So this is a composition where the outside function this time is the cosine, and the inside function is the sine inverse of x. And since the inside function, we are taking the sine inverse of just x, we won't need chain rule with the sine inverse. So the derivative of cosine is negative sine of the inside left alone. Then we're going to multiply it by the derivative of the inside, so the derivative of the sine inverse of x is 1 over the square root of 1 minus x squared. So then, whenever you have sine and sine inverse performed together at the same time, they can cancel each other out, leaving you with negative x over the square root of 1 minus x squared. Now for this next one, I didn't leave the directions here. We're going to be leaving our answer exact for this one as well. We're going to be calculating the derivative of the cosecant inverse of e to the x plus 1, and we're going to evaluate it at x equals 0, leaving our answer exact. So because we're leaving our answer exact, we do need to do this by hand. So we're going to start with finding the derivative function for the cosecant inverse of e to the x plus 1. Now clearly this is a composition where the cosecant inverse is the outside function, and e to the x plus 1 is going to be the inside function. So keep in mind that the derivative of cosecant inverse of just x looks like this. So if you are taking the derivative of cosecant inverse of anything other than just x, right here and here, in for both of these x's, you will have the inside function left alone. So the derivative of the outside is going to be negative 1 over the absolute value of the inside left alone times the square root of the inside left alone squared minus 1. Then we're going to multiply it by the derivative of the inside. Derivative of e to the x plus 1 is e to the x. Now this isn't going to simplify any more than this, so let's just take that derivative function, and then we are going to evaluate it at x equals 0 by plugging 0 into every single spot that we see in x in the derivative function. So that is going to be negative 1 over the absolute value of e to the 0 plus 1 times the square root of parentheses e to the 0 plus 1 squared minus 1 times e to the power 0. And e to the power 0 is equal to 1. So that is equal to 1, that is equal to 1, and that is equal to 1. So we get negative 1 over the absolute value of 1 plus 1 is 2, times 1 plus 1 is 2, 2 squared is 4, minus 1 is 3, and then times e to the 0, which is 1. The absolute value of 2 is 2, so we have negative 1 over 2 square root of 3. And if you want to rationalize this, you just simply multiply both the bottom and the top by the square root of 3, which gives you negative square root of 3 all over 2 times 3 is 6. And then that is going to be your final, fully simplified, exact answer. So then looking at this next one, we have the function x times the tan inverse of x over 2. And we're going to be evaluating f prime of 2 square root of 3. We're going to evaluate it by hand, and we're going to leave our answer exact. Leaving your answer exact requires you to do this by hand. Now, overall, this is a product. Overall, we have x times the tan inverse of something. So this is going to be a product where x is the first part of the product, and tan inverse of x over 2 is the second part of the product. Also, keep in mind that if you are taking the tan inverse of anything other than just x, it does require the chain rule. And x over 2 can be rewritten as 1/2 x to make your derivatives easier. Now, if you take a look at the tan inverse of just x is going to be 1 over 1 plus x squared. If you are taking the tan inverse of anything other than just x, its derivative is going to be 1 over 1 plus the inside left alone squared. So this will be the overall structure for the derivative of the outside function, except right there where that x is, you will have the inside left alone. So let's start with the derivative function f prime of x. So derivative of the first part of the product is 1 times the second part of the product left alone. Then we're going to add to it the first part of the product left alone times the derivative of the second part of the product. So the outside function is the tan inverse. The inside function is x over 2, which you can write as 1/2 x to make your derivative of the inside easier. So the derivative of the outside is going to be 1 over 1 plus the inside left alone squared. Then you're going to multiply it by the derivative of the inside. Derivative of 1/2 x is 1/2. So then just because, we are going to be evaluating this at something and I do want to make this a little bit saner, let's simplify a little bit. So we've got the tan inverse of x over 2 plus I'm going to put that x in the numerator and I'm going to go ahead and write this as 1 plus x squared over 4 times 1/2. Remember, when you take a fraction and you square it, you simply square the numerator and square the denominator. So then what I'm going to do is I'm going to evaluate the derivative at 2 square root of 3 by plugging 2 square root of 3 into the derivative function into every single spot that I see in x. So I've got the tan inverse of 2 square root of 3 over 2 plus 2 square root of 3 all over 1 plus, I'm going to use parentheses here, 2 square root of 3 squared over 4 times 1/2. So quite a bit does simplify here. So first of all, those 2's cancel each other out, and that 2 times 1/2 also cancels each other out. So that leaves us with the tan inverse of the square root of 3 plus square root of 3 over 1 plus. Now when you take 2 square root of 3 and you square it, you can simply square both parts of the product, because if you have a product raised to an exponent, you can simply raise each part of that product to that exponent. So 2 squared is 4. Square root of 3 squared is 3 all over 4. Now for the tan inverse of the square root of 3, what this is asking is what function gives me a tangent of the square root of 3, and that is pi over 3. Plus, this will be the square root of 3 all over 4 times 3 is 12 over 4 plus 1 gives us 4. And that is exact enough. If you want to combine them into one fraction, you just find common denominators. But you can do that if you want to. This is good enough for a final answer. So remember, if at any point in this video you want to attempt a problem on your own, just feel free to pause the video and then resume when you are done working. So for this next one, we're going to be finding the equation of the line tangent to the graph of this g of x at the point 1 comma pi over 3. And we're going to be leaving all answers exact here. Now, to find the equation of a tangent lines involve derivatives. So to find the equation of the tangent line, you need the point of tangency, which we have, and you need the slope of the tangent line. Since we do not have the slope of the tangent line, we're going to find the slope of the tangent line first. And since we are going to make sure that our answer is exact, we're going to find the slope of the tangent line by hand. So to find the slope of the tangent line, you start with taking the derivative. So we're going to be taking the secant inverse of 2x. Now, if you have anything other than just x inside of your secant inverse, it is going to require the chain rule. So this right here, this derivative rule right here, is the secant inverse of just x. And that's going to be 1 over absolute value of x times square root of x squared minus 1. Now, if you're taking the derivative of the secant inverse of anything other than just x, the derivative of the outside is going to follow this overall format, except right there and right there, and for both of those x's, you're going to have the inside left alone. So for the derivative, the outside function is the secant inverse, and the inside function is the 2x. So we're going to start with the derivative of the outside. So the derivative of the outside is going to be 1 over the absolute value of the inside left alone times the square root of the inside left alone with parentheses around it, squared minus 1. Then we're going to multiply that by the derivative of the inside. Derivative of 2x is 2. All right, so let's simplify a little bit. So, 2 and 2 can cancel each other out, leaving you with 1 over the absolute value of x times, and I'm going to go ahead and simplify this 2x squared by squaring both parts of that product. So 2 squared is 4, x squared minus 1. So next, I'm going to evaluate this derivative function at the x-coordinate of the point of tangency 1. So I'm going to take my derivative function, and I'm going to plug 1 into every single spot that I see an x. So this is going to simplify as 1 over absolute value of 1 is 1, and then 4 times 1 squared minus 1 is the square root of 3, which you can simplify / rationalize to the square root of 3 over 3. So this right here is the slope of the tangent line. To find the equation of the tangent line, you need to combine the slope and the point of tangency into the equation of a line, and you can use point-slope form. So y minus the y-coordinate of the point of tangency, pi over 3, equals slope of the tangent line, square root of 3 over 3, times x minus the x-coordinate of the point of tangency, 1. And if you have to write this in slope-intercept form, you just distribute square root of 3 over 3 and then add pi over 3 to both sides. So then for this last one is going to lead us into one of the major applications of derivatives, which is in quantities that are changing. In any real life situation, whenever you have something that is changing and things that are in motion, odds are they are not in motion in isolation. In any real life scenario, there are going to be multiple quantities that are all going to be changing they're all going to be changing at the same time, and they are all going to be functions of the same variable time. And in a lot of real life scenarios, there might be some quantities that are not changing. And if you have any quantity that is constant and not changing, you can go ahead and use it because derivatives involving constants are really easy to find. So in this situation here, which I have a little picture for you guys, as the sun descends behind a 150-foot grandstand of a baseball stadium, the shadow of the stadium is going to move across the field. So this shadow length S is going to be moving across the field this way. L is the line segment between the edge of the shadow and the sun, and theta is the angle of elevation of the sun, the angle between L and the horizontal. The length of the shadow is the distance between the edge of the shadow and the base of the grandstand, and it is given by S. So in this picture here, we have S, which is the length of the shadow. We have theta, which is the angle of elevation, and we have the grandstand. The grandstand is 150 feet. So before we even dive into either part of this problem, what we're going to do is we're going to first look at, all right, what is changing about this scenario, and more importantly, what is not. So as the sun sets, is the shadow length going to be changing? Yes, the shadow is going to be getting bigger. As the sun goes down, is theta going to be changing? Yes, and so is L. What's one thing about this problem, though, that is not changing? The one thing about this problem that is not changing is the height of the grandstand. The height of the grandstand is this fixed 150 feet. So for part A, we're going to express theta as a function of the shadow length S. Now, whenever you are relating your variables in an equation, you don't want extra variables. If the problem only calls for theta and S, the equation that you come up with should only have theta and S. Which means that line segment L has nothing to do with theta and S, so we're going to try and write an equation that relates just theta and S without involving L at all. So let's at least find a relationship between theta and S. Now S is the adjacent side of this right triangle, and theta is this angle of elevation. We do not want to involve L because L is an extra variable that the question isn't asking for. But we do have this constant, 150 feet. So let's use it. Now, what is the relationship between this angle, this side S, and this side 150? So the 150 is the opposite side. S is the adjacent side. This is a tangent ratio. So I'm going to express this relationship as the tangent of that angle theta is equal to the opposite side 150 divided by the adjacent side S. Now this problem did specify to express theta as a function of S. What that means is we want theta equals something something s. So we want theta by itself. So how do we get rid of tangent and get theta by itself? No, you do not divide by tangent. To get rid of tangent and get theta by itself, we are going to take the tan inverse of both sides. So I'm going to take the tan inverse of both sides of this equation. So when tan and tan inverse are performed together at the same time, they're going to cancel each other out, leaving you with theta is equal to the tan inverse of 150 over s. So there is your function theta expressed in terms of the shadow length s. Now for part B, we're going to be computing d theta ds when s equals 200 feet, and we're going to explain what this rate of change measures. So we are going to be calculating a numeric derivative. I can't show you on this same video because if I try to open two programs at once with the screen capture going, I'm going to crash my PC. So I did post a video on how to evaluate a numeric derivative on a calculator, and I will leave a link to that video in the description. So you can go ahead and use a graphing calculator to evaluate the derivative function at s equals 200. The variable you're going to use is the same generic variable button for any other feature on the graphing calculator. In this case, you use x. And just keep in mind, the default units for any angles are radians. So unless the problem specifically specifies that theta is in degrees, the default is radians. So since nowhere in here did it say that theta was in degrees, make sure that your calculator is in radians. So you are going to be calculating, d, in this case, x of the tan inverse of 150 over x, evaluated at x equals 200. And you should get approximately negative 0.0024. So just take a moment and make sure that you get that, and leave some room. We're going to interpret this. First of all, why is the derivative negative? Remember, if you have a negative derivative, that means you have a negative rate of change, which means since this is the derivative of the function theta, this means that theta is decreasing. So as the shadow length increases, theta, the angle of elevation, is going to decrease. So here's your interpretation. When the shadow is 200 feet, the angle of elevation is decreasing at a rate of, and here's where you need to make sure that your derivative has proper units, and this is one advantage of Leibniz's notation. The derivative is going to have a unit that involves the word per. It is going to be the units for the numerator per the units of the denominator. So it is changing at a rate of 0.0024. The units for theta were in radians per. The units for the shadow length were feet. So when the shadow is 200 feet long, the angle of elevation is decreasing at a rate of 0.0024 radians per foot. So that is it for the derivative rules, and that is going to be it through the material for the second exam. So all of the derivative rules will be on the second exam. Now after this, now that we've covered all of the derivative rules, after the next exam, we are going to be looking at more applications of derivatives, because now that you can take derivatives, now we can go using derivatives in a variety of contexts. And the next context that we're really going to apply derivatives to is in related rates, which is very similar to this type of problem here, where you have multiple quantities that are all changing with respect to one independent variable, time. So thank you all very much for watching, and I will see you in the next section where we start applications of derivatives.